Hello, my name is Sophia Payne, and today I'm going to be talking about Lab 3, the magnetic field of a bar magnet. The purpose of this experiment is to measure the distance dependence of the magnetic field of a bar magnet and observe how the magnitude of the magnetic field changes as we increase and decrease the distance to the observation location from this magnetic field. For this experiment, we will need a bar magnet and a phone magnetometer app. Our magnetometer will allow us to observe the real-time values of the magnetic field generated by the bar magnet as we move the bar magnet further from and closer to our magnetometer. Note that it is important to indicate where the magnetometer chip within our phone lies to ensure that our measurements are accurate. To begin, using only the magnetometer, we are going to place our phone wherever the X contribution of the magnetic field of the Earth is as close to zero as possible. This will ensure that we're measuring only the contributions of the electric field of the bar magnet and not the contributions of the Earth's magnetic field as a whole. Once this step is complete, we're going to measure the distance r at which the magnetic field has a magnitude of 20, 70, 120, 170, and 190 microteslas. We will then determine the distance dependence of the bar magnet's magnetic field. We will do this using our Excel graphs line of best fit formula and formulas 2 and 3 indicated on the right to calculate K, mu, and the distance dependence of the magnetic field. Finally, we will use ClosScript and Biot-Savat's law to find the magnetic field at 45 degrees at a distance of d, and we will compare predicted and observed magnetic fields at this location. This slide shows the results of my on-axis magnetic field experiments. The equation for my line of best fit, y equals negative 2.8763x minus 14.077, is equivalent to the formula ln(bz) equals ln(k) plus n ln r. My value of negative 2.8763 is my experimental distance dependence, which is relatively close to the expected value of negative 3. The y-intercept of my line of best fit, negative 14.007, is equivalent to ln k. When you solve for k, this gives us the value 7.69 times 10 raised to the negative 7. To solve for mu, I use the formula to the right. This gave me a value of 3.46. My experimental findings for measurements of an electric field at a 45-degree angle at a distance d are also included in the slide. My observed magnitude is equal to 4.17 times 10 raised to the negative 5 teslas, and the vector for the magnetic field is equal to 6.86 times 10 raised to the negative 6, 2.59 times 10 raised to the negative 5, 0 teslas. This ClosScript code finds the magnetic field at a 45-degree angle at a distance d. This code uses Biot-Savart's law and our previously found magnetic moment, remember mu equals 3.46, and rotates the coordinate system to account for the rotation of the magnet, and accounts for the magnetic fields of Earth in order to determine the magnetic field at this location. Here are the results of my ClosScript code. This code created a magnet with arrows being the magnetic field. The orange arrows are on axis, the blue is on the vertical axis, and the purple arrows are at a 45-degree angle. My magnetic field at a 45-degree angle at a distance d is equal to 9.8 times 10 to the negative 6, 2.9 times 10 to the negative 5, 0 teslas. This electric field has a magnitude of 3.097 times 10 raised to the negative 5 teslas. This is significantly lower than my experimental result, which had a magnitude of 4.17 times 10 raised to the negative 5 teslas. These differences are likely due to experimental error or interference from other electronics. However, the overall findings of my experiment still have merit. As expected, when the magnetometer was far from the magnet, the x directions had a near zero electric field. As the magnetometer moved closer to the magnet, the x component would increase. However, if my experiment wasn't oriented to compensate for magnetic north, my results would have changed due to the principle of superposition. The Earth's magnetic field would be having an impact on my magnetometer, making the net magnetic field inaccurate. If two magnets were placed together end to end, then the strength of the magnetic field would almost double. It doesn't actually double as the magnets cannot occupy the same space, and due to the increased distance from the second magnet to the observation location, it will not perfectly double. Thank you for listening to my presentation.